Alright, so let's continue on the bearing selection. Okay, so we'll finish the bearing today, and then we'll get on to the screws, power screws, and threaded fasteners. So what we were at the end of the last lecture is second case, basically selection bearing under combined loading. Okay, so combined loading meaning you have both an axial load and the radial load acting at the bearing location. So the idea is to come up with an equivalent radial load Fe, such that the Fe does the same damage as the combination of the Fa and Fr. The formula to come up with the Fe is this particular one here, XIVFR plus YIFA. Xi and the Yi are the so-called radial and thrust load factor, and it depends on the value of I. So I can be 1 or can be 2. So the 1 or 2 depends on the ratio comparison, the ratio Fa and VFR, and the so-called E factor. So E is called the limiting factor for bearing selection. And table 11-1 is basically our guidelines in terms of this selection process. So you have a column here for I equal to 1 and the columns here for I equal to 2. And then you have a column of E value corresponding to the ratio between Fa and Fr. Now, the problem, as I mentioned, is at the beginning we don't have a bearing, so we wouldn't be able to identify what X and Y value for our calculation, right? So what we have to do is we have to start somewhere within the table, and most of the cases will start for certain Y value at somewhere in the middle, and then we can iterate through a few steps to come up with the actual decision for the bearing. Okay, so this is example we started. Given Fr and Fa of this much, so Fa is smaller than Fr, right? And sometimes Fa is so small, and you could basically just end up with a situation that neglecting this Fa, consider the whole thing as a radial load only. The RPM is this much, and design life of 20,000 hours. Already determining on the minimum shaft diameter of 3.1 inch. With load factor and the reliability factor as 1. Okay, so in this first step, first method, I would call it, let's call it first methods at here. Okay, the first method here we started with Y2 equal to 1.5. So that's kind of a decision by observation at here. So 1.5 is somewhere in the middle of these column values, right? So if you start with 1.5 and you calculate the Fe, the equivalent load Fe, which you got 2,149 pound force, then we can substitute into the load life equation for the bearing. So we'll be able to get the required dynamic load rating value. So this is the value we will have to use when we look up a bearing from a catalog. So let's say we decided to use an NSK catalog, and we decided to use a 03 series. Inside this is 03 series ball bearing. We pick the 16 ball size, and 16 millimeter ball size basically is the size that's marginally bigger than 3.1 inch. Okay, so that's the first even from the first iteration, we picked this bearing. We got from the table here, the bearing has a dynamic load rating of 27,600 pound force. And for the same bearing, the static load rating is 19,500 pound force. Okay, so let me maybe open up the bearing. So this is the 6316 bearing, and that's the C10 and the C0 reading corresponding to this bearing at here, right? Okay. So with this bearing C naught and the FA is given, so we can calculate the ratio between FA and C naught at here. Okay, so that turned out to be 0.0346. Okay, so now let's see the next step, 7. Okay. So if you go to step 7, basically you go back to the table 11-1. What do we get the ratio? We got a ratio for FA over C naught is 0.0346. So that's a value between 0.042 and 0.056. So somewhere between, right? Between 0. So somewhere between this, right? So 0.0346, somewhere between this. And the E value, you can take a look at. Well, that's the next value 0.22, next value 0.424. So you don't really need to do any linear interpolation. You could just from here just say, okay, so E is approximately 0.23. Okay, so that's the E value based on the selected bearing at here. Okay. Now once you get the E value, then we'll look at the ratio between FA and VFR. So basically, we'll look at the ratio of this. We'll compare to the E, whether that is going to be this column or this column for our next step. Okay. Yeah. So this ratio at here, 675 over 1850, and that's approximately 0.36. So this is definitely bigger than the 0.23, right? 0.23. If this is greater than E, then basically means we're going to take I equal to 2, or in other words, the thrust load cannot be neglected. Okay? Yeah. So step number 9 now, okay, is what is the Y2 at here? Okay, what is the Y2? So if you look at the current, basically FA over C naught, from the table, here's a 0.028, 0.0346, 0.042, right? And the corresponding Y2 for this one is 1.99, for this one is 1.85. So the question is, right, what's the Y2 corresponding to this particular value at here? Okay. And here you need to do linear interpolation at here. Okay, so you need to use a linear interpolation. The interpolation formula is y equal to ya plus x minus xa, and then yb minus ya over xb minus xa. Okay, so substitute, this side is x, this side is y, so substitute this x into here. Xa, let's see this guy here, xb would be this, so that's how you can interpolate. Okay. So the results of the interpolation is 1.924. Okay. So we got the Y2 now, so then that's step number 10 is to recalculate the FE and the CREQ. Okay, so recalculate the required one here. FE is equal to x2 VFR plus y2 FA. So this time we have exactly y2 value. That gives us 2,334 pound force. And with the updated FE, we can recalculate the C required. So LD over L10, 1 over 3. and this one give us 25985 pound-force. Okay, so updated C required is this much, and this value still less than the selected. Right, it's still less than the selected C10 value for the 6316 bearing. So basically means the 6316 is okay. So this essentially means with 2 iterations, and we're okay with the original basically selection 1663 here. Okay, yeah. Is that clear? Okay. So this is the first approach, right? First approach is I started with y2 equal to 1.5, okay, and we actually able to decide on the bearing with basically 2 iterations, right? Yeah. Now I want you to also let's try a little bit of a different approach here. Let's say from the first step, right? Instead of starting the y2 at 1.5, how about we start the y2 at 1.0? So if you look at this table here, right? If you look at this table, the smallest value for y2 is 1.0, right? And you can start from the 1.0. That's a very extreme value here. Let's say in this particular case, right? You can try this, okay, and you will still end up with a 6316 with 2 iterations. So not much difference. Okay, so not much difference here if you try this method. So just to start the y2 with the different values here, right? Different values. Okay. Now the third approach, okay, I also want you to try it here. Okay. So basically at the step 1, okay, so instead of starting with a certain y2 value, the third approach we're going to do is, well, let's just use a trial and error. Let's start with the bearing. Okay. So which means we're going to start with a bearing here. Okay, so we'll start with the bearing. Now starting with the bearing, this is tricky because the only question here, it tells you is the minimum shaft diameter, right? Now the bearing, when you pick a bearing, there's so many different dimension series, and we use 0.3 in the previous 2 methods. There's also 0.2. There's also other dimension series. Every dimension series has a ball size with a 16 millimeter, basically, right? So which one do we pick then, right? And you do know that the higher dimension series it is, then the higher basically the catalog rating value would be, right? Okay. So let's say basically you have a 0.2 and a 0.3 series, for example. Okay. So I'm gonna start differently. Okay. So let's say we start with 6216. Okay. Let's start with 6216 here. Okay. So if I start with 6216, and we can take a look at the catalog, okay, from 6216 and here. So 6216, you have this much of a C10 and a C0, right? So you got a C10 with 16,300 pound-force, and C0 is 11,900 pound-force. So that's 6216 at here. Okay. So once we find this here now, then we can, step number 2. So we can calculate the ratio between FA and C0. And this gives us 0.056. Okay, 0.056. And then step number 3, from this table, same table, we got our E is approximately 0.26. 0.26. Okay, and then step 4, okay, we can calculate the ratio between FA and VFR. So 675 over 1850. It's the same value, 0.36. Again, it is greater than the E value at here. Okay, it's greater than E. So your I is still going to be 2. Step 5, we will recalculate the equivalent force. Okay, so you can recalculate the equivalent force, right, based on the updated I equal to 2, and that gives us 2190 pound force. So if we do a recalculation of the C required, okay, with the formula, so now this time we got 24282 pound force. Okay, 24282. So you see now the required C required is what? It's bigger than the bearing, right? Bigger than C10 corresponding to the peaked bearing here. So that's bigger than this much. Okay, that's bigger than this. If it's bigger than this C10, so which means 6216 is not good enough, right? So then, technically speaking, you're going to have to go to the next choice, maybe 6219, right? So you're going to have to try 6219 here. 6219 may be okay. So 6219 maybe it's a 24,500. So maybe okay. Okay. But you see the difference is, right? If you go this series, then you end up with choosing a bearing 6219 millimeter. If you choose 6219 millimeter for the bearing has a ball size 19 millimeter. So what does that mean for the shaft? The shaft has to what? Has to bump up, right? The shaft size has to bump up to 19 millimeter at here, okay? Because the shaft has a minimum requirement, which is 3.1, very close to 16 millimeters, okay? So if you choose this, then you have to bump up the shaft size by a little bit, okay? By a little bit, okay? Bumping up the shaft basically means a little bit bigger size. This means probably a little more expensive, okay? So this is actually why, basically maybe you should try 6003 series, right? 03 series, okay? Yeah. So you see the difference that here, right? When you try a different starting point, you end up with a different number of iterations, basically, okay? Yeah. For this trial and error approach, it probably means more number of iterations than the first and the second approach. Okay? Yeah. So it really depends the iteration. Okay. Yeah. So just bear in mind of how you get started, and also the choice of the starting point. Right, make quite a bit of difference here. Okay. Okay. So that's basically the two different scenarios for choosing a bearing or selecting a bearing. One is when you have completely radial load only, and the other is when you have a combination of radial and a combination of radial and thrust load. Okay. Yeah. The last knowledge point for the bearing is there's one more here, so we'll be able to finish this. We have another scenario called variable loading. Okay. So in particular, we're going to look at piecewise constant loading. Okay. Piecewise constant loading. So I'll present a case to let you know what does it mean by variable loading or piecewise constant loading. So here is one very common scenario. Okay, So let's say you have this side is it's the load at here. Okay, this side is the load. So you're going to subject the bearing with initially a load Fe1, and you're going to subject the bearing under this load for a duration of L1 number of cycles. See the difference now, right? Previously what we have been considering is the bearing is subject to one load for the whole life, right? So however number of cycles it will last is subject to the same load. Now this time the bearing is subject to one load, okay, under L1 number of cycles, and then afterwards subject to Fe2, okay, for L2 number of cycles, and then Fe3 for L3 number of cycles, right? So this is one type of a so-called piecewise constant loading situation right here. Okay? So let's say afterwards, then you repeat this pattern. Okay? So let's say after this L1, L2, L3, and then the pattern will be repeated. So essentially, it go back to Fe, F2, F3, and then Fe, F2, F2, 3. Each time is always L1, L2, L3. Okay, yeah. So pattern, keep repeating this pattern until when? Right, until the bearing failed. Okay, until the bearing reaches its life. So now the objective is, okay, the question basically is, let's find the number of repetitions, okay, of L1 plus L2 plus L3, okay, before failure. So that's the idea. So how many repetitions of this pattern, right, until this bearing reaches ultimate life? Okay, yeah, and that's the last case that here we wanted to learn it here. Okay, so how do we approach this? So here's the solution. Okay, recall the load life equation. This is the load life equation. The load and life are subject to this expression right here. Okay, so if we rewrite this equation, right, basically take a power to the power of a on both sides, so we get F E to the power of a n times L equal to a constant. So constant to the power of a is still constant, right? Yeah. So I'm going to call this constant capital K at here, okay? Capital K. So this equation here, now if you recall, the equation basically means is subject the bearing to a load Fe, and the bearing will fail at this much number cycle L, and then you have this expression equal to a constant. Okay? Yeah. And I can consider basically the K here as a concept of a damage. So this constant is like a damage. When you reach this ultimate damage value, then the bearing life is gone, right? Yeah, so that's the idea. Okay, so but now the specific situation over here is you subject the bearing to Fe1, right? To Fe1, and you only subject to L1, right? Number of cycles. Okay, which basically means the bearing is still healthy. Okay, it's still good. There's still life remains for the bearing, but when you subject this to this much here, guess what? There's certain damage being accumulating, right? So we'll call this is basically certain damage at here. We'll call it the damage D. Okay? So we can call this is damage D in here. Let's call it D1, right? Is that good? Yeah. So you can imagine for Fe2, L2, there will be D2 damage. For this one here, there will be D3 damage. So ultimately, when you repeat by one time, right, when you have this pattern, repeat the pattern one time, then how much damage is done for the bearing. So you have this much damage done for this, and this much damage done for the L2, and this much damage done when it's L3, right, and F3. So this is how much damage done, right, given given the one pattern, right, given repetition of one pattern here. And let's say call this is basically di, and I equal to 1, 2, 3. So you have 3 damages: d1 plus d2 plus d3, right? Okay, that's the damage. Okay, so, but I wanted to really rephrase this slightly different. Okay, rephrase it differently. So, which means what I want to do is I want to find an equivalent force. Okay, find equivalent force which will do the same damage to the bearing when you subject the bearing to this FEQ and also subject bearing to this duration of L1 plus L2 plus L3. That makes sense, right? So this situation is you have 3 different piecewise forces. Okay, but I wanted to find an equivalent of force subject to the same force under L1 plus L2, L3 cycles. So, and then do the same damage. That's why I use the equal sign. So both sides will have the same damage here. Okay. So now you can see L1, L2, L3 is given. So we can solve for FEQ, right? So FEQ can be solved, which is okay. If you solve for the FEQ, that's the solution, right? So that's what you get for the FEQ. And this FEQ will do the same damage within L1 plus L2 and L3 number cycles here. Okay? Yeah. So if FEQ do the same damage as the combination of F1, FE2, and FE3, then the next question is, so how long does the bearing last, right? So how long, right, does the bearing, okay, last under FEQ, right? That's the point here. Okay, so, and this is very easy. If you have the bearing and you can choose the load life equation to calculate. So that's how long the bearing will last, completely the same, under the same force FEQ, right? Under the same force FEQ here. Okay. That's how long the bearing will last. If the bearing can last this much longer, L at here, then all we need to do is use L, okay, divided by L1, L2, and L3, and this will give us the number of repetitions. Okay, right. So that problem solved. Right. Okay. So one little bit extension from here, okay, just one little bit extension, basically, like one of the Simon questions asked you to do in for this week is this. So let's say we slightly modify the question a little bit. So this is FE1, and this is L1, and then FE2, and then L2. Okay, so same thing as the previous example, but now what we do is we subject to FE3. Okay, we don't change anymore. Basically, subject to the FE3 for the rest of its life. Okay, for the rest of its life. So this until failure. Okay, until failure here. Okay, so that's the situation here. So the question here is, okay, what will be the remaining life? Okay, remaining life equal to what? Or L3 equal to what? So that's another example, right? So instead of repeating the pattern, we don't repeat. So it's just subject to the first, second, and then constantly subject to a third load for the rest of the life. Okay. So let's see, how do we solve this kind of question here? Okay. So let's use a similar approach as we just did here. First of all, when you subject the bearing to FE1, okay, and under L1 number of cycles, here is the much of a damage, right? This is basically a damage concept. Okay. This much damage has occurred, and then FE2, L2, that's another how much damage, right, is caused under this much load. And finally, you have FE3 and L3, right? So this is another much of damage. Okay. When you add all the three things up according to the scenario, right? You have this damage 1, damage 2, and damage 3. So technically what we see is it reached its life, right? That's according to this diagram here. So this total, when you add this up, this is basically the total damage concept. Okay. When you add this up, you reach the total damage. Okay. Yeah. Good. So the key value is the total damage. It's the total damage at here. So now I'm going to divide K on both sides. So we get K at here. Okay, so we'll divide the K for both sides at here. Okay, so we get this equation. Now, the key is the concept of total damage, right? This is total damage. Now, total damage meaning what? You load the life equation. Let's say if I subject to FE1, and it probably will last for L1 number of cycles, and that equal to the total damage, right? And if you subject to FE2, it may last a total of L2 number cycle. That's also a total damage. If you subject to L3, and this is also the same total damage at here. And this one is also the same if you have the bearing selected and you have the Satan value for the bearing. And this is basically still the total damage here, right? See, all of these are total damages, okay? A total damage here. If you picked the bearing already, you can literally calculate the capital L1, capital L2, and a capital L3, right, based on this expression. So basically what I'm going to do is I'm going to substitute into here, okay, substitute each one of the K, okay, into this expression at the top over here. Okay. So as you can imagine, once you substitute into this expression at here, you actually cancel out all the load terms, right? You cancel these load terms out. Okay, you cancel this out, and you end up with just L1 over capital L1, L2 over capital L2, and L3 over capital L3 equal to 1. So we have L1, L2, capital L1, L2, L3 can be calculated, okay? So then you can solve for L3, which is so that's the example, not a specific example, but when you have this kind of a scenario, that's how you can calculate the remaining life L3 at here, okay, given the repetition of L1, L2 under FE1 and FE2. Okay. So let's take a look at a quick example here. It's very much the same as your assignments. Okay. So in assignments, you have FE1 equal to 18 kilonewton, and you have FE2 30 kilonewton, and subject to FE1 under L1, okay, 200,000 number cycles. And what will be the remaining life, okay, when you subject the bearing to FE2? Okay. In this case, suppose we choose a 0 to 30 ball bearing with a C10 equal to 20.3 kilonewton, and L10 is 10 to the power 6. Okay, so now to solve this question, first step we do is we need to find out if you subject the bearing purely under FE1 or FE2, then how many number cycles will they be able to last? Okay, and that's the equation you use to calculate capital L1 and L2, and the capital L1 calculated to be this much out of here, and L2 would be this one. Okay, kind of makes sense because FE2 is bigger than C10, right? So you end up with a less than 10 to the power 6 number cycles. Once you find L1 and L2, then you can use this formula that we just derived. This formula has L1, L2, L3, but in our case we only have L1 and L2. So you actually can simplify, so then you don't need this term in here, right? So we can have L2 equal to capital L2 minus 1 minus L1 over capital L1. Okay. So substitute everything into this formula. This gives us 0.267. So we have around 267,000 revolutions left, okay, or number cycles left. Okay, is that good? Yeah. So this is a very simple calculation here, okay. And sometimes I'll test this one here very simply as a multiple choice at here, because this you just have to remember this formula in terms of calculation the remaining life, okay, of a bearing here. Okay, so that's all about bearing. Okay, we practically just finished. There's a branch, if you recall that, basically the branch on the rotational to rotational machine elements. Okay. Yeah. Any questions? Yes. Which one? Oh, the small a. A is 3 for ball bearing, right? And 10 over 3 for rotor bearing, basically. Yeah. Yeah. Okay. Very good. Okay. Now let's start the new topic at here, which is the screws and ball screws. Okay. Because of I'm going a little bit slow this term, so I'm going to use the PowerPoint here to speed up a little bit in terms of this section here. Okay. Okay, so let me just so let's look at a few facts about screws and fasteners. Okay. The objective of the learning in this section is basically we want to be able to interpret and specify thread forms based on existing standards, to develop an understanding of power screw mechanics. Okay, so essentially the relating the force and the torques when you're using power screws. We also I also need you to be able to identify the stress, the type of stresses essentially, or even combination of stresses, particularly in the power screw. Okay. This is a little bit less than in terms of the calculation. It's more just to identify. You will see that. Okay, identify the stresses at the different locations on a power screw. This is the diagram and I showed you a few times already. So we're looking at essentially two different locations in here. Okay, so the fasteners is over here. Okay, power screws is over here. Okay, so take a look at the details. Okay, so here's the first question, right? Take a wild guess. This is a Boeing 747 airplane. How many fasteners do you think that have been used to build this Boeing 747? 2 million? Very close. 2.5 million. Yeah. So some of the screws, that doesn't include even the rivets yet. Some of the screws cost a few dollars each, right? So I guess you can take a guess how expensive to build an airplane, basically, right? So the fasteners are small elements, but that's so crucial, right? That's something to hold the whole system together, basically. Okay? So choose the right one and design for the right one. That's very important. Okay. Let's take a look at the anatomy of a thread, okay? And we'll also look at basically some terminologies that are here. Okay. First of all, when you see the threads on the screw, okay, mathematically, basically, it's a helical curve. Okay? So it's a helix going around and going above. Okay? So when you have a helical curve, and one of the terminology called a pitch. So basically, that's the distance, okay, between two crests. Okay, that's the distance between two crests. That's called a pitch. Okay. There's another term called the lead. Okay, the lead is not exactly the same as pitch. Okay. And it really depends on the type of the thread. So you can have a single thread. You can also have a double thread. You can even have a triple threads, right? Yeah. So the lead at here. If a single thread is basically the same as the pitch, but if a double thread, then the lead is 2 times the P. Okay? If a triple, then 3 times P. Okay? When you have a screw at here, 3 important parameters called the major diameter, mean diameter, and the minor diameter. Major diameter refer to the diameter basically when you measure the diameter from the one side of crest to the other side of crest. So that gives you this major diameter. Okay. Minor diameter basically when you measure from one side of the root to the other side of the root, so you get this minor diameter. And mean diameter is somewhere in between. Okay. That's the 3 important parameters that are here. Especially this major diameter. Okay. So if you go to a Home Depot, to a machine shop, and then when you buy a screw, okay, so the 2 important parameters that you will identify, one is the major diameter, one is the pitch. Okay. So root is this location, and crest, of course, is the top location. Okay. Yeah. H refer to basically from root to the top. That's called the thread depth. Okay. The angle called thread angle alpha here, and alpha is essentially we'll take it as a 60 degrees. Okay. There is another angle called lead angle lambda. So lead angle lambda is more of a concept related to helical curve. If you draw a vertical line and then you look at the inclinations of the line here, so you get basically the lead angle. Lead angle is y minus, it's 90 degree minus the helix angle. Okay, yeah. Helix angle is another concept related to the helical curve. So lead angle you can also think about like this. If you unwrap, right? If you unwrap the thread, okay, by one turn, for example, if you unwrap that, okay, from the cylinder, from a cylindrical body, then you end up with basically a ramp, right? Inclination angles, and that angle give you this basically the lead angle lambda. Okay? That's how you can interpret this. There are two different standards, basically defining this thread. One is the so-called unified standard, and the other is so-called the metric standard here. Okay, yeah. So they have a different protocols to define the two different type of profiles. Okay. Unified, of course, in inch. Okay, and the metric is, of course, is in the metric. Okay. So I'll show you the difference set here. The first profile is called the basic thread profile. It's applicable basically to the UN or M class. Okay. So basic profile, as you can see here, it shows you basically the external thread and internal threads. Okay. Over here, essentially the dimensions are labeled according to this all the straight lines that are here. Okay, so this straight line separates the internal and external threads. Okay, and the dimensions are given over here. So you have h, which is from one end. That's the thread depth, right? And h is related to the pitch, because of this is basically the equal side triangular triangle at here. So you can calculate the h in terms of the pitch easily, which is √3/2 times p. Okay, and based on the dimension, you can get the relationship between minor diameter and the major diameter and the p, and mean diameter and major diameter and the p. Okay, yeah. So this is basically the so-called the basic thread profile. Okay. But in our textbook, okay, there are two tables. There's one table is called table A-1 and A-2. So that two table will give us the profile for metric and also for the unified standard. Okay, so this is the so-called metric, basically ISO profile. The difference between this one and the basic is the root at here is a rounded root. Okay, so it's a rounded root here. Okay, so that does change this calculation of the minor and the mean diameter slightly, and you can see this is a d minus 1.22. Here is 1.08. So there's a slight difference. You can very easily identify how this is calculated, purely simple geometry. Okay, if you look at the unified profile here. So the difference is for the ISO profile here, the distance between the end of the root and this crest location is h/6, but for unified standard, it's 1/8 times h. So that's the only difference that here. But that slight difference resulted in the different expression for dr and dp. Right, the minor diameter and mean diameter. These two formulas, actually, you can find them in the footnote for table A-1 and A-2. Okay, so these two formulas. I'll show you the tables shortly here. Okay, but let's look at another concept that you can find from the table. It's called the tensile stress area. Okay, tensile stress area, basically, we'll use this one actually for our later calculation when we design for threaded joints. Okay, so essentially the tensile stress area calculated is defined as you use the mean diameter. Calculated, okay, between the dp and the dr as the area for the tensile stress. Okay, so basically you don't use just the minor diameter dr for the calculation of the area, right? So like if you cut a cross section, you feel like, okay, so dr is the minimum area, but when we design for the screw, the tensile stress area, so the AT is calculated based on this formula here. Okay, so that's dp plus dr. Okay, the average value between these two. Okay, so then sigma t is if you have any force applied, okay, in the direction vertical along the direction of the screw body, then you can just use the force divided by the tensile stress area, so you get this tensile stress essentially. Okay, yeah. So that's the calculation of tensile stress area. Now, often in time, you actually don't need to calculate this. You can use the following two tables to find the values, okay, for AT. So this is the table A-1, just the part of the table. So you can see the table give you two different series. One is called coarse pitch series, and the other is called fine pitch series. Okay, yeah. So if you look at the most left-sided here, that gives you the so-called the major diameter D. Okay, and then the second column here give you this pitch at here. Okay, give you the pitch. So and then the tensile stress area is given over here. Okay, it's given over here, right? Yeah. And for the fine pitch, the tensile stress area is given. So this is somewhere you will you will be given, let's say, specify the screw. Then this is the column here. You can look up for the tensile stress area. Okay. So same thing for the UN series. That's table A-2. Okay, here's the size corresponding to certain major diameter, and then here is so-called thread per inch. Okay, thread per inch. So the 1 over this n will give you the pitch essentially. Okay, so thread per inch is, and then you use 1 divided by this column here will give you the pitch, and then you have this tensile stress area AT at here. Okay. As I said, you could have multiple threads, okay, situations. In that case, your lead will be the number of threads times the pitch. Okay. So this is the illustration of double thread and a triple threads at here. Okay, yeah. So you can see grain, right, separate by 1. So grain, you have the grain 1, 2, 3. So that's triple threads. Okay. For the threads, you can have either right hand or the left hand is. Okay, so there are two different basically directions. Okay. The way it works basically for the right hand, if you turn it clockwise, you'll go basically to the right side, right, and this one, right, will go to the other direction. Okay. Yeah. So that's the difference between right hand and the left hand. Yeah. The other way you can identify is just like a gear. You can put the screw on the top of the flat surface, or you can just look at it like this way here, right? If it's right hand, then it's inclined to this way. You have a right hand rule like that, right? Otherwise, you have the left hand direction of the thread. Okay. Okay. So another important skill is you need to be able to interpret some of the important informations, okay, given the thread specification. Okay. So this illustrates. I'll give you two different examples here. Okay. So for this example here, and my pointer only shows up on my side here. Okay, this should be okay now. Really? Give me a second. Why is the pointer not working? Okay. So let's just do it this way here. Okay. So if you look at this example here, this is basically a UN standard profile, and it shows there's 1/2-20 UNF 2A and LH. So the first number here is called the major diameter, so that's basically 0.5 inch as the major diameter here. And the second number here is called thread per inch. So 20 thread per inch basically means what would be the pitch for the thread at here. What's the pitch for the thread if you have a 20 thread per inch? What's the pitch number or pitch value? thread per inch. The pitch is 1/20, right? Yeah. So you got a 0.05 inch, okay, for this particular screw here. And UN, that's the UN style, UN profile. F means it's a fine, okay, so it's fine series. And then it's 280 here, it's sort of the classification for the tolerance and a fit, okay. And last two digits here refer to whether it's left hand or right hand type of thread, okay. Yeah. And this one here shows you examples for metric, okay, example. So it starts with M and then 6 times 1. So 6 basically here refer to the major diameter, and 1 refer to the pitch diameter. So that's not diameter, it's the pitch value, okay. So that's good. So this one directly give you the pitch value. Okay, so 1. 5G, 6G refer to the tolerance basically for the pitch diameter and the major diameter. Okay, and last one here, of course, is same thing. L is left hand or right hand basically. Okay. Yeah. So if I particularly later when an example, okay, you probably will give just an example. Just say, okay, you have a screw of M6 by 1. So you should be able to interpret that, okay, so 6 is a major diameter and 1 is a pitch, right? So that has to be able to be extracted. You may not be specifically given the pitch value for the screw, okay? Yeah, so you need to know that 1 is the pitch. So let's take a look at shift our attention a little bit to power screw right here, okay? And some of the terminology is particularly related to power screw. Power screw is a device that's used in machinery to change angular motion into linear motion while transmitting power. Okay? And it's very common, type of machine elements that you see. Okay? Everybody in their car has a jack, right? So that's basically power screw. You probably will have used a clamp. It's called a C clamp. So this portion is also power screw right here. For one of the experiment probably did in the material science, you may have a press machine or tensile machine, okay, and chances are you have a power screw type of mechanism, okay, to do that type, to transmit that amount of basically power here, okay. And there's another type of power screw basically called lead and ball screws, and I'll show you, okay. This is basically a power screw used in the lathe. Okay, so you have a lathe lead screw right here. Okay, for this particular type of power screw, the thread is so-called the profile of the thread is the so-called ACME thread. Okay, so we'll look at that shortly. What does ACME thread means to us? Okay, what's the typical numbers associated with ACME? This is another type of power screw. It's called lead and ball screws here. Okay. This is a very actually smooth type of power screw mechanism. So you have a nut, and within the nut there are a number of balls, okay, circulating basically inside the track. Okay. So the contact between the nut and the screw is basically through the balls here. It's like a bearing basically. Okay. So it's very smooth rolling motion, right? Very smooth rolling motion. Just comparing to the sliding motion as a typical ACME type of power screw, right? Yeah. But you got to be careful though, right? Don't let the balls fall out. If the balls fall out, then you won't be able to put it back. Even if you put it back, then you won't be able to be as smooth as it is. It is a very typical thing in many robotics applications when you have a so-called prismatic arm. So the arm basically extend and retract. The motion to basically for that type of mechanism. So you have a motor connected to this. Let's say the nut right here. So the rotate of the nut will cause a linear motion along this the axial direction. Okay. Yeah. So it's a very useful thing. It's normally very expensive. So there are two different types of power screw threads here. One is called the square thread. Essentially, the thread is square here, right? And the other type is called ACME thread. The only difference is ACME is not a square, and there is a thread angle. The thread angle is a 29 degree. Okay, so this is not like that 60 degrees as a typical screw there. Okay, yeah, and P is the pitch. Okay. The height of the thread is 0.5 p. Okay, so that's standard. You can change that. Okay, so this is basically ACME thread and square thread. So what we want to do next is, okay, let's say we have an ACME thread or a square thread type of power screw. We want to have a little bit understanding of the mechanics, okay, associated with the power screws that are here. Okay, yeah. So first of all, just a little bit of terminologies here. So if you have a power screw, okay, apparently you have a nut sometimes. Okay, work with the power screw right here. You can either rotate the nut to raise certain load, okay, or lower the nut to lower certain load to a certain load. Okay. Same thing. You have a pitch. You have a mean diameter, and there will be a lead angle for a power screw. There will be a helix angle, so same like the typical screw thread, right? And F is the axial compressive load. Okay, so that's the load. You either lowering it or raise it. Okay, so the question here is how much of a torque do we need to raise the load, and how much torque do we need to lower load? Okay, for the different type of screw thread. Okay, so that's the idea here. Okay, so let's quickly go over some of the free body diagram here. Okay, so this is actually really nothing new right here. So let's say you have a square thread. Okay, and if you on-thread one turn, okay, basically if you unwrap one turn of the thread, then you get a ramp, right? You get a ramp. And the ramp has a lead angle lambda. Because it's one turn, so you have basically this much of distance pi dm when you unthread one turn. And one turn, basically you go up this much of lead distance, which is L. Okay. If it's a double threaded, then L times 2p, right? If it's a triple threaded, then L times 3p. Okay. So let's say this is the load you're trying to raise or lower. If we're trying to raise the load, then free body diagram, you have the F right here, trying to put a force PR, trying to push it up. Okay, and then you have the supporting force N. You have a friction on the surface. So the friction times the supporting force give you the friction force. So that's basically the free body diagram right here, right? Once you have the free body diagram, the next thing is easy. You just create equilibrium equation in two directions. One is vertical, the other is the horizontal direction. Okay, so then you can solve for you can solve for the solution for the PR. Okay, for the PR here. And here is the similarly basically for when you have a ACME type of thread. So if you're ACME type of thread, the only difference, the the surface of the thread, instead of a flat, then you have a little bit angled here, right? So this is basically the angle here, okay? And this is the end at here now. So when you look from the front, looking from the front view at here, this is the front view, then the free body diagram, right? It's slightly different. This is n times cosine alpha instead of the previously. It's just the n over here, right? It's just n. It's just the n over here, okay? Yeah. So now you have n times cosine alpha. And same thing, you can create a free body diagram to basically calculate the amount of force that you need to raise or lower the load. And once you find the force, then you can calculate the torque by using the force times half of the mean diameter. So because say you're using the force, and this is applied to the mean diameter at here, circle. So this value times half of the mean diameter, you get basically the amount of load torque need to raise up the load, and also the amount of torque that needs to lower the load at here. Okay? Yeah. So if alpha equal to 0, right? If alpha equal to 0, then you get the solution basically for this particular situation, square type of thread. Okay? Yeah. And to add on just a little more here, there might be friction at the collar location, so you need an additional basically torque to overcome the friction force caused the torque. Okay, so that's to overcome the torque, the collar friction. So overall, your formula for the amount of load to raise and to lower, which is this formula here. Okay. So I just want to touch upon one thing at here about this. Okay, so let's take the just maybe one little bit knowledge here. Now see is let's see for square. Use a square thread, okay, to illustrate the concept here. Okay, so for square thread, the TL will be F times dm over 2, and F pi dm, okay, minus L pi dm plus FL. Okay, so without friction, right? Let's see, without friction, okay, the TL to lower the load is this much at here. Okay, so why I want to try to point this out is this. So if you take a look at this formula in here, right? On the numerator here, you have basically F pi dm minus L, this term. Okay, you have this term here. So for this term, you can literally see this term could be what? Could be less than 0, right? This term could be less than 0 here. So what does this term less than 0 mean? So what does this this is the torque that you need to lower the load, right? This is the torque you need to lower the load. For certain situations, somehow this term could be less than 0. Okay, could be less than 0 here. And this less than 0 physically means what? So you have let's say you have a nut right here, right? And you have a certain force right here. Okay, in order to lower it, somehow this torque becomes, if this is less than 0, then this torque becomes less than 0, right? Or less than 0 means, do you even need to apply a torque to lower the load? Exactly, right? Even with that load, the nut basically will drop by itself, right? So this essentially is the so-called non-locking. Okay, so it's a non-locking situation. Okay, if this is less than 0, it's non-locking. This is very common, right? You know, especially if you play with that lead and ball screw. And if you raise it up, it actually will return and drop by itself, just because it's so smooth, right? Very small friction. Okay, so there's no locking, self-locking there essentially. Okay. And the other thing is, if you look at this one here, it has a lot to do with the L, right? So if L is big, then there's a chance that this term is less than 0. And L is the lead. Okay, L is the lead at here. And what's the lead? When you unwrap one term, that's how deep, right? That's how steep the ramp goes up, basically. So you can imagine if you have a higher lead L, then you should have a higher chance of getting a non-locking situation, right? Yeah. So if this term is greater than 0, so then you get basically a self-locking basically situation. Okay. Yeah. Okay. So in terms of the formula, this is basically the overall formula for TR and TL at here. Okay. For TR and TL. Okay. Another concept. I'll just use this one in here. Okay. Another concept before we look at an example is the so-called power screw efficiency. E. Okay, power screw efficiency E. E is defined as the amount of work output work over the amount of work in. Okay, so you can simplify it to be W out over W in. That's the efficiency. Okay. So how much work that's input that has been given to the power screw then? So you apply a torque TR, right? You apply a torque TR, and let's say you apply the torque TR and trying to rotate the bar, the handle, by 360 degrees. So TR times 360 degrees, that's how much work that you input into the system, right? Okay. At the same time, when you rotate the nut by 360 degree, okay, so the nut will travel vertically this much of a lead distance L, and because you're raising up the load F there, right? Raising up the load F. So the amount of work out is F times L. So that E basically becomes FL over 2 pi times TR here. Okay. So this is the power screw efficiency E value. Okay. So let's take a look at the example quickly, okay? Still have a few minutes over here. And I'll use a square thread, okay, as for this example. Square thread basically referring to a thread type like this. Okay. And the thread is always P over 2, so that's pitch divided by 2. From here to the other side, you get your mean diameter dm, and from here to the other side, you get your major diameter d, and the dm equal to d minus p over 2. Okay. So mean diameter equal to the pitch diameter, the major diameter minus the pitch over 2. Okay. So let's say for this particular thread, we have our major diameter equal to D equal to 24 millimeter, and pitch equal to 5 millimeter. and dm equal to 24 minus 5 over 2, which is 21.5 millimeter. Okay. So let's say suppose we're trying to raise the load F equal to 3 kilonewton. Okay, so and then it does, the thread has so the thread has a friction coefficient F equal to 0.09. Okay. The collar has a friction coefficient Fc equal to 0.04, and the collar has a mean diameter, let's say 33 millimeter. Okay. Yeah. So if you look at the formulas I showed you here, okay, so this is basically the formulas inside here. This F is the friction on the surface of the thread, and this is the friction at the collar location. This is the collar here, and the DC is the mean diameter for the collar location, okay, as a DC location. So basically inside this is the formula. We're using this formula here, right? In this formula, okay. As for squared thread, then alpha equal to 0 degree. Okay. Okay, so based on this given at here, let's consider a few things. Okay, and then we'll calculate a couple of things here. Okay. First, case 1. Let's consider single thread first. Okay, let's consider single thread. If it's single thread, we got L equal to P equal to 5 millimeter. So then we can calculate our TR. You can calculate TL too using these formulas I showed you over here. So you can calculate this one here, plug in all the numbers. You get TR equal to 7.22 Newton meter, and this is 2.49 Newton meter. Okay. So overall, you'll get your power screw efficiency, which is 0.33. Okay, so this is for single thread. Okay. And let's calculate another one. Let's take a look at the case number 2. If we have a double thread, double thread basically means L equal to 2P equal to 10 millimeter at here. You can calculate the similarly TR and TL. Okay. So as a matter of fact, if you neglect the collar term, your TL will actually become a negative number. Okay. And that's exactly the case. And I was saying, for this particular case, see the lead is bigger, then it becomes non-self-locking here, right? If there's no collar. So this time you can calculate the efficiency, power screw efficiency, which is 0.49. Okay, 0.49. And this is a pretty obvious, right? It's pretty obvious. Basically, for double thread, you have a higher efficiency, okay? But it increased the chance of non-self-locking, basically. Okay. Yeah. And we'll take a look at an example in the next lecture. But any questions? Okay. Good.